Hey, John here. Let's look at our memory again, right? We got text. These are your executable instructions. We have data. That's initialized data. BSS, uninitialized data that's set to all zeros. Then you have the heap and your stack. Stack is where activation records go, right? Records. And the heap, we've yet to talk about the heap. The heap is used. What we do is we allocate things, and we say, look, I need some memory to use for an object, and that will get placed into the heap. As we allocate more and more objects, the heap grows upwards. As we call more subroutines, the stack grows downwards. All right, as long as these don't collide, you're fine. And if you have a 64-bit system, the number of bytes from the bottom here at 0 to the top is 2 to the 64th power, which is somewhere around 10 to the 19th power, in decimal. So that's an incredibly huge amount of space. So my point is, this is not drawn to scale. This part down here is really probably as thin as this little line, as thin as this little black or the dark outline on this bar on the bottom of the page. Okay, so this is like, 10 to the 15 or 16th power more than you see down here. Point is, there's a huge amount of space in here. Okay, so how do we use the heap? Why do we use the heap? Well, the simple fact is that if you allocate something that's a local variable in a subroutine, like function f, right, and you've got, maybe I got an object called foo, and I create one in here, and I'm going along, this f returns, this foo, the lifetime of this variable extends to the duration of the execution of this function f. As soon as I hit this close curly or there's a return instruction here, the activation record for f goes away, and with it, this f goes with it, because this f is placed inside the activation record for this function call. All right? Now, that works great, provided that you only need, the lifetime of these variables needs to only be for the duration of each one of the functions within which they're created. You can also put them in the data section or the BSS by making global ones, right? So outside of a function, I could say foo f, and I could make a global one, right? Global variable, or ecstatic type variable. And it'll be put down here in the data section or the BSS if it's filled with zeros. And this can be arbitrarily large as well. But what if you don't know how many you need? Like I need to allocate an object for each element I might be reading from a file or something like that. Well, you're never going to know. I suppose you could pre-allocate an array that's bigger than anything you'd ever need. Yeah, that's going to work. And you'll always need one more someday. And if you only need 3 of them and you allocate 1 trillion in here, you're using up so much memory that your program will take forever to do anything, even if it only has to process 1 or 2 elements. So that doesn't work either. That's what the heap is for. The way the heap works is you can say, rather than make this foo instance, this variable f, and put it in my activation record, I can say put it in the heap and then leave it there. Since it's in the heap, when this function leaves and its activation record goes away and the stack goes up, the foo down here will stay around. It stays around forever in that scenario until someone explicitly deletes it. So I can allocate it in this function. I can let, maybe I can return a pointer to it, or set some variable somewhere else so that other functions somewhere else can still know where it is and use it. And then this function can leave and it'll stay there. All right, that is enormously useful. That's how most data is allocated in a program that has any dynamic nature to it of any kind. And most programs need this sort of thing. So what are the details here? Well, the details are that we use these operators called new and delete, and these are actually operators, even though they look like keywords or functions and stuff like that. So it's new and delete. I suppose you can guess that new creates a new one, right? Of whatever I want to create, a foo or something like that. Or I want to say delete one, remove one of whatever's being deleted, okay? Now, the way you use these is like this. Let's say I got this function f and I want to create a foo, but I don't want it to be in my activation record. I want to like return a pointer to it or something like that. So I would say, a foo. If I'm going to return a pointer to it, I have to say foo star to declare this pointer. And if my function f returns a pointer to a foo, I end up with a function whose signature looks like this. Inside here, I might say star, maybe I'll call it p. I can say then p equals new f. This new f does the same exact thing as this foo f, but rather than putting it in the stack, it puts it in the heap. No other difference, okay? After that, I can say return p, and I'm done. Once this finishes, the address of this new f, right? Let's say the new one is allocated in memory right here. This p, this new f, will be that memory right there. Explicitly, it's not up here in the stack. I can then return the address of this block of memory that holds the value of this f object to anyone who wants it in a calling program. When I'm done with this thing, I don't have to come back to f to remove it. Anything, anywhere that has the address of this object can use the delete method, or the delete, I should say, operator to get rid of it and unallocate this memory, so to speak, so the memory can be reused for something else. So how does that work? If I have a foo pointer, maybe I call this f function to set it to something. I say foo p equals f, okay? So I call function f allocates 1. It does a new on 1, returns the address, and I set it my local variable maybe in some other function over here to remember where it is. I might do some work on it, and then later I can say delete p. This is how I remove the element from the heap. All right, let me put a box around that so that we have nice little examples here. All right. So let's write some code and see how this works. All right, now we've seen this before. Here's my foo class from, I don't know, we were talking about classes or something in a previous video. It's got two private member variables. It's got a default constructor and an overloaded one that allows us to set these variables to some other values. The default simply uses the list initialization here that just says, oh, I want to set them both to 0 unless I'm told otherwise. The destructor simply prints a message out, and of course the constructors also print out a message on their way to doing their job. I got a couple of functions here that we've implemented that print some stuff out. A couple of mutators and an accessor. We've seen all this before. This is the exact same code from my previous discussion. So let's add a couple of functions here and see what happens. If I create a foo object on my stack, I can obviously pass a pointer to it to some functions, and those functions will use it, and it'll work. Everything will be fine. It's fine as long as you remember the name of the program. So as you recall, the constructor prints out the address where the thing is that's being constructed, right? So here's my foo. I then call like tf1, and tf1 calls this func. And then I called tf2, and tf2 calls a func with a double, and it prints some stuff out, and ultimately it has a destructor because it goes out of scope of main down here, right? So there's the constructor getting called there. tf1 goes in here. You saw it call func with no arguments. Then we call tf2, which causes the func to run with the double, all right? Just to exercise this a little bit. Now let's go on to this one. Same class, same code, same member functions. There's my TF1 and TF2. Now let's look at what's going down here. Let me make a nice row of asterisks so we can see what's going on here. Don't get too confused. The only difference is I've created these two functions. These are not methods of the class. Class is no change in any way. Here's one called broken as designed. I hope that you can understand that this is supposed to fail, and it's not an example of anything you would ever want to do in a million years. Here's another one called get a foo, and we'll look at what these do in a second. First, let's look and see what's going on down here in main. This actually does not invoke these functions right now. It just goes to TF1 and TF2 like we did before. So let's change this main function now. Let's call both of these functions and see what happens, okay? Let's call this broken one, and then let's talk about why it's broken, okay? Actually, we don't even need to call it. As you will see, the compiler will complain about it. It's so bad, even the compiler says no, okay? Star P equals that thing. Okay, let's first talk about this broken one, all right? Here's a great example of something that you're not supposed to do. So I print out, hi, I'm in the broken function. I'm entering the function. I'm going to create a foo object. And this foo object, because it's a local variable, is in my activation record. And then it says, okay, I'm done now and I'm going away. And I'm going to return the address of this F object, which technically is legal. It exists. It has an address. I can assign that address to a variable. I can return that address if I'd like to. But even the compiler knows that this is completely incompetent, okay? Because why? This foo is about to be destructed. It'll be automatically destructed when it goes out of scope. We've already discussed all this, okay? What is the scope of this variable, right? It goes out of scope when the curlies are exited. When you leave the curlies within which it is defined, it will be removed and destructed because it's in the activation record. So let's go ahead and compile this and see what the error message is we're going to get from the compiler. Warning, address of local variable f is returned from this function right here. Don't do that. And oh, by the way, here's the one that you're doing that you shouldn't be used. Now it's going to gripe down here because I added this code to main that says you have a variable that you never used. That's fine. We'll use it in a minute. All right, so what's the point of all this? Don't do this, okay? If 0, get rid of this bad code. Even the compiler says no. All right, now let's move on to the one that is not broken. So what is this going to do? He's going to say, hi, I've been entered. I'm going to do new foo, just like I showed you in the hand sketch. I've got a pointer variable to remember where it is. So new, you could think of it as an operator that materializes the value of a pointer to the thing that's created over here. All right, now I said new foo with empty parentheses over here. That'll call the default constructor that has no arguments. I could, if I wanted to, I could put the variables in there if I wanted to, right? Like 1 and 5, right? Why? Because it has two constructors up here. It has an overloaded constructor right here. Now we'll call this one. So I don't use the default, which sets them to 0. I can set them to 2 and 5, all right? So let's go ahead and do that just to mix it up a little bit. Anyway, so yes, the new operator will yield the value of the address of that new thing that's just been constructed. All right. Then it says I'm leaving from the get a foo routine, and I'm going to return the address of the thing that I created in the heap. Perfectly legal. In fact, you don't want to forget where it's at. That's a problem. We call that a leak. It's leaking memory, right? You're forgetting where the things are if you throw this pointer away. And that can be a huge problem because after a while, if you create enough items and never destroy them, and never delete them, then you will eventually run out of memory. It'll just fill up with a bunch of unusable items. Okay, so we've got our foo created, and we returned it, and main gets it, stores it in a variable called p. And the compiler knows that we've done this for no useful reason and generates a warning. So let's do something useful with it. We have a pointer to a foo. So what can we do with a pointer to a foo? We can call one of these functions or something like that. We could call... let's call this function up here. What does that thing do? It just prints out, hi, here I am, and here's the values of the member variables. We've seen this in other discussions. Now, let's leave a bug in here. we're still leaking, right? Right? We've allocated one in the get a foo routine. We have done a new on one. We return its address to main. Main uses it. Hi, I'm going to call this function over here. Then main leaves. At the point main leaves, P is a local variable. P, the pointer, goes away. But no one ever deleted the object it was pointing at that came from getAFoo. So I don't think the compiler will complain about this. This is where things get really difficult if you don't know what you're doing, okay? It compiled without any warnings, and I even have wall set. It will run. In some perverse sense, it is okay, because when main leaves anyway, your program's done anyhow. Does it really matter that you've left these things undeleted? It would depend what they are, and it would depend on what deleting them really means. More often than not, this is considered, in fact, I would say almost 100% of the time, this is considered incredibly bad practice. It works, is not good enough. Now let's look and see what's going on here. So getAFoo was entered. You see the constructor with the two integers get called. You see this number here. You'll notice it's significantly smaller than the number over here, because why? It's in the bottom of the heap rather than the top of the stack, okay? Then after that is constructed, it says getAFoo is leaving. We know that this address is returned back to main. And main hangs onto it in a variable that it calls P, and then it calls P func. And that P func, rather the foo func method over here, when it's running, it prints out its own address, and it tells you the A and B variable values. So this is how you can create an instance of an object in a subroutine and share it with some other one that does not have, like common ancestry kind of thing. Now, you could say the main is the ancestor of getAFoo, but maybe you've got another function over here that's called useFoo, and he needs a foo to do something. So basically, he assumes that something somewhere before this is invoked created it somehow, either on the stack or in the heap, it doesn't matter, but this guy needs one. And he might call P right arrow func, like this, right? Let's go ahead and put some little messages in here. We can again track what's going on. useFoo is entered. useFoo is leaving. And this is what I mean by, this function here is using a foo instance that was created in another function, in this case over here, that is not an ancestor of this one. Okay? In other words, the thing it's using was not created and stuck on the in the stack of its caller or some grandparent or great grandparent type of function up there. So let's remove this one and instead call useFoo. Now we're writing real C++ code here. Create some stuff, use some stuff. I'm still going to leave the destructor out in this example. All right, what's happening? Oh, this is so much noise on my screen. There we go. So getAFoo is entered. Right, because he's going to make one. So he makes one, and that's the address it's going to be at. He then says he's leaving. Main then calls useFoo and passes him the address that was created in getAFoo, which you can clearly see is the same object because it has the same address. And you can see that the values are still there and all this other stuff. useFoo is then done and gone. And you don't see the destructor called yet because nobody destroyed it. Now we want to, oops, I'm hitting random keys here, sorry. Now, let's say main is done and we want to do the right thing. You say delete P like this. All right. Now you're going to see that this is cleaned up. So let's go ahead and add a little bit more noise to our output. Main is entering. And by the way, I do this all the time when I'm trying to learn how something new works. you'll see, if you ever see any of my code, it'll be littered with all kinds of little things like this, all commented out or, half cleaned up. Usually I don't clean them all out, but I will comment them out because you certainly don't want all that noise coming out of your program when it runs for real. All right, so here we go. Main is entered. He calls get a foo, so he's entered. He creates them. He returns the address. Use a foo is entered, and we saw this last time. You'll see this address changed from the time it ran before. Okay, C1FF2C0 versus whatever up here. That's fine. You're going to end up with different things every single time. Then what happens? Then it calls use a foo and it prints its stuff out. Use a foo goes back to main. Main calls delete and gives it that P, and then main says, okay, I'm done, and he returns. Okay, this is really all there is. Okay, there's only one other topic that we need to go over here. There's a special case for arrays of objects. Okay, I mean there's not a lot of funny business going on here. This is simple, but that actually makes it difficult at the same time, right? Because, how do you really use this? And the answer to that is that, it depends on your application. What else is new? So the rest of this whole course will be on what you're supposed to do with these things, okay? So half the course gets us here. The other half will be going from here forward, all right? So let's go ahead and get rid of this broken garbage out of here. It's just going to be, it's embarrassing. We don't want to see that. We don't ever want to admit that we've ever written such a heinous and disgusting thing. Now, first let's do this. Let's do a foo with no arguments at all. Okay? This, I argue, is the same as that. All right? Let's make sure that I'm not lying and run this as it is now. Okay? The fact that it compiles with no warnings is a good sign. Okay. So he goes in to get a foo. A foo is created. It comes in here. Func then is invoked in the use of foo. And because I removed those parameters, it was constructed with these the member variables inside the foo object were set to 0 because the default constructor does. Now it's leaving and main destroys it and so on. It's no shock there. Only thing I really changed was the fact that I used this constructor instead of the other one. And I showed you that you can create it without the parentheses. Now let's do something else. What I was getting at was arrays. So let's look at this. P equals, I'm going to set this off here. There we go. New foo 100. I can allocate 100 foos. That's a lot. Let's just do 4. You'll see why in a minute. 4 foo objects. And the reason you're going to see why in a minute is because it's going to construct all 4 of those. And remember, we're printing stuff in those constructors, and it will spew for an hour and a half if we create too many. So we don't need, we just need a plurality for this presentation. Now let's run this code right now and see what happens. The key here is there's something dubious now about what does it mean to delete an array like that. Okay, let's just allocate the array and let's run this and see what happens. See if I'm lying or not. No, I'm not lying. Ooh, look what's going on down there. Okay, so what happened? You can see 4 of these get constructed. Right? Why? Because I asked for 4, and I asked for them in the form of an array. And we all know that an array is laid out in memory one object after another. Now, this particular object has 2 member variables. They're both integers. Those integers are 4 bytes each. Therefore, the total amount of memory consumed by the instance of foo is 8 bytes in hex. 8 is, halfway to the base, which is 16. So you're going to see C8, D0, D8, E0 for the beginning addresses of each of those object instances. So this all makes perfect sense. This is a whole array of foo objects starting at the address here that ends in C8. That then goes back to main. Main passes that pointer that it got from get a foo, which makes perfect sense. It's the address of the first element in the array. That's what you get when you have when you're talking about arrays. Remember, the array represents the address of the first element. So func doesn't care. It has a pointer to a foo. It's the first one, but it doesn't know, nor does it care. It then calls the func, and we see the zeros in there. Why? Because the default constructor put zeros in there. He then leaves. Then we call delete on C8 here. And then main dies before he does anything else. Why did he die? Well, you could say I used the wrong delete operator. If you allocate an array, you need to delete an array. Oops. You have to put square brackets like this. If you put square brackets on there, then the delete operator knows that there's an array of items in there. It's not just one element. It's a whole array of elements. Now look what happened in here. It's deleting them backwards. In C++, the variables are allocated in the order in which they're specified in the function. Like if they're local variables, you got A and B and a C, they're allocated in that order, A, B, C. When they're deleted and removed out of the activation record, it goes backwards, CBA. And that happens for array elements as well. C8, D0, D8, E0. And the array notation for delete deletes this last one first. And then it goes further, 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 back to the first one. It always does it in reverse order, okay? Now, there's a reason that is useful. It's not necessary in this particular case, but at certain times, the order in which things are created, sometimes future objects might have pointers to the objects that existed before them, right? So the last thing you'd ever want to do is kind of pull the rug out from under the feet of something. So by default, C++ tries to help you that way. If I create an object A, and then I create an object B, and an object B here knows about A. It has a pointer inside of it, maybe, back to this A. It would be nice to get rid of this thing first. That's what's going on here, okay? So by default, C++ does that. Now, why did I get a core dump? That actually is probably a subject of a different lecture that has to do with memory allocation and the confusion that the compiler has to deal with if you tell it the wrong information, because I don't know if I can explain it in one sentence, but I'm going to try here. It has to do with the fact that, remember what I said in the heap, when you delete something that's sitting there, it has to free up that memory and make it available to be reused, okay? That's one of the things that delete tries to do. Well, if you tell it to delete something and you give it the wrong kind of thing, it doesn't know how to delete and free up that memory, okay? So what happened here is that core dump occurred while it was trying to delete it because it didn't do it the right way. You deleted one element instead of all of the elements, and it misjudged how much memory it needed, and it failed, and it got a seg fault. So let's look at this. All right, in the GDB, just for fun. Do that if it's fun to you, I don't know. But, and I want you to see this because what happens is this will happen in your program. This one's obvious. Why? Because I did it on purpose. We know exactly. It's the only delete that happens anywhere in the whole program, and we're printing out all this information. We know exactly what it was doing when it died, okay? But let's say it's buried in the middle of your program. You got 80,000 lines of code in 57 files, and it's going along, and you get a core dump, and I don't know where I'm at. Well, again, run GDB and say where. Well, look what's going on here. See this libc free in malloc.c. If you know about C and how the operating system manages its memory in the lower level libraries and stuff, that malloc and another thing called free are the lower level libraries that are used inside of these constructors and these, not the constructors, but new and delete rather, I should say. Internally depend on malloc and free. So whenever you see this thing going on about, I'm trying to free up memory, now you know, it died in a destructor. Okay, and it died on line 98 of classes 3 in main, right? So let's go ahead and quit. Yes. What am I on? Line 98. And once again, we're back to our delete function, okay? So, it's dying in some library you didn't write. I didn't write it. That's an operating system provided library, okay? How are you going to debug this thing? You got to track it back to who the lowest line and the deepest part of the call stack in your own program where it failed should be the clue. And in this case, because I allocated an array and I deleted a single unit, I've created myself a problem. All right. Now that's the whole thing in a nutshell. That's really all there is. You're either allocating and deleting one, or you're allocating some plurality of them and deleting that plurality. You'll notice you don't put a number in here. Okay, the delete function figures it out on its own, and it's not that smart. That's actually why it died down here. It can't know how many there are if you don't give them a clue that says there is a plurality. Once you tell them there's a plurality of elements in there, it will figure out how many there are, where they are, and delete them all. But you need to give it a clue, all right? From here on, it's just a matter of now determining how many of these things you want to create in your application and how to coordinate all this stuff so that you don't do things like forget how to delete them and when to delete them. All right? So thanks for watching. See you next time.